Hello everyone, welcoming you all to this session to discuss about the topic interconnection structures. So in the previous session we have discussed about the various multiprocessor organization, and now we will just discuss how these processors are going to be interconnected with each other. As such, we have different structures available. Few of them are listed here. The first comes under the category time shared common bus. So here, as the name implies, we are going to have a common bus, and it is going to be shared across different processor with the appropriate time quantum. The second one is referred as multi-port memory. We have multiple connections, and through these ports we will be connecting the memory with the respective processors. And then we have crossbar switch, then the multi-stage switch network, and then the hypercube system. So in this session we will discuss all these interconnection structures one by one. So as such, in the multiprocess system, we have the CPUs and the IO processors which are connected to the input-output devices and the memory unit. This is going to be the components, and we have to connect all these components. We can have multiple processor, and there could be some dedicated input-output processor. They are different from the CPU in a way that if it is CPU, it is meant for processing, and all the IO processors are meant for taking care of IO activities. So there could be multiple CPUs, and similarly there could be multiple processors, IO processors, and these processors are responsible for transferring the information between the input devices and the memory. So they will be connected to the input output devices and the memory unit. So the interconnection structure will differ from each other based on the number of transfer paths that are available, and also the configuration which we are going to make use of. So we will have the connections between the processor and the memory, and all these processors can share the memory, so it can come under the category shared memory system, which is also referred as tightly coupled system. And if you take connections across the processing elements alone, so these processors can have some local memory attached to it, and such type of processing elements can be connected with each other in a loosely coupled form, meaning that there is no concept of sharing the memory. Instead, everyone will be having some dedicated memory. So if it is going to have a dedicated memory, then how they are going to communicate with each other? Each processing element will be communicating with another processing element by means of passing some messages. So we have some message passing mechanisms that will take care of communicating the one processor with another processor. So the different forms of networks, as I listed in the previous slide, the same thing is listed here. So we will just see one by one. So to start with, we have the time shared bus. I think this can be clearly explained from this diagram here. Maybe the time shared common bus is shown here. So we have the bus here, which is going to connect the memory unit, the CPUs and the IOPs. If it is going to be a common bus, this common bus is going to be shared by all these processors to communicate with the memory. So at what time and how long a processor can make use of it, that is going to be decided by the time sharing. So it is called as time shared. So the total time it is going to be shared across the different processes. And since we have the sharing of memory, so this will come under the category of tightly coupled system. And if you just observe this diagram, see here we have a common system bus, and this is a common shared memory. So this shared memory is going to be communicating with the CPU here, IOP. Here also we have CPU, IOP, CPU. So all these processors and IO processors all will have a common shared memory. Apart from this common shared memory, if we just observe separate clusters, here we have the CPU and IOP, and these processors can have their own local memory. And if at all the CPU wants to share with a common memory, they can establish a communication by means of a system bus controller. So the purpose of the system bus controller is to provide connection between the common shared memory connected to the system bus to the local bus. So we will have separate bus structure to provide communication between the CPUs and the local memory. And if at all a processor wants to share some item with the common memory, they have to interact with the system bus. So these processors can interact with the system bus with the help of the system bus controller. So we have this arrangement like this. Every CPU and IOP will have their own local memory connected by the local bus, and if they need to get connected with the common shared memory, they have to do it with only the system bus controller. So like this we can have different set of arrangements, and all these local buses will be connected to the system bus. So that's what we mean by dual common bus system. Here what we mean by dual common bus, we have a system bus that is also common to all, and we have the local bus that is also common. So it is at the innermost level and it is at the higher level. So we have different levels in which the processors are going to share the memory at the local way or at the global way. And the link to each local bus to the common system bus is always controlled by the system controller. And why we call it a tightly coupled system? If they are going to have a common memory, it is going to be shared and it is going to be called a tightly coupled system. If they have their own local memory and if this local memory is not going to be shared across the other processors, then it is going to be classified as loosely coupled systems. Okay, so the first connection time shared bus we have just discussed now, where we have local bus and common bus system bus, and sometimes if it is going to be limited in number of processors, they will have only one global connection. So your common bus is going to be connecting all the processors and the memory unit, and that's what we call as a common path. There will be a common path existing. So what is the problem with this? Here only one processor can communicate with the memory or it can communicate with another IO processor in a given point of time. If more than one device wants to communicate, they will end up in a conflict. So who has to use the bus and how long they have to use the bus will be always decided by the controller, system bus controller. In this setup, we have the system bus controller, whereas in this setup, there could be some processor dedicated as a master processor, which can decide how long the remaining process can make use of the common infrastructure. As a consequence, if you just observe here, the overall transfer rate of the system is going to be limited by the speed of the single path, because that single path is going to be shared by all the processor, and that is going to be a limitation. And a more economical implementation of the dual bus structure is shown in the figure here. So by means of this local bus and the system bus, common bus, we are able to cater to different number of processes and more number of processes. And here the part of the local memory may be designed as the cache memory attached to the CPU. So we have also discussed the concept of local memory. This local memory can be referred as a cache memory, which is a high speed and an expensive memory. And maybe if you go to the common shared memory, it can be a normal memory. So I think this completes the discussion of this common bus structure, which is time shared bus. And if you just observe this diagram, the same thing whatever we have discussed so far, it is given in this form, where we have the local bus connecting the local devices with a local memory, and we have the system bus that connects to all the processors and all the components, which is going to be connected to the common shared memory. Then the concept of, then we will discuss about multi-port memory. So the first category time shared bus is over. The next concept of discussion is multi-port memory. So what actually we mean by multi-port memory? Here we have multiple port structure. So the first diagram, figure 13.3, this is going to refer to the multi-port. So we have the CPUs arranged in one column and all the memory units arranged in different columns. Each CPU will be connected with all the memory modules, and similarly these memory modules also will have one-to-one connection with all the processors. So this connection is going to be established by means of multiple ports, and at any point of time any processor can interact with any of these memory modules. So the advantage of this type of structure is high transfer rate, because they are going to operate independently and they are not going to share the bus. The efficiency or the speed of transfer is going to be very high. But the drawback is it is an expensive memory, a control logic, and large number of cables and connectors. So as we have seen the diagram, we have to provide separate connection between the CPU and the memory as a one-to-one connection, and it may demand some extra complicated hardware, and that can also end up in an expensive, costlier option. And also we have to have a control logic which will decide that who has to be connected to which module. Suppose if the processor wants to participate, to connect, or wants to communicate with the memory 1 and memory 2, then the control logic only will open this connection and they will be able to communicate with each other. So the main advantage is the transfer can happen in parallel, and the problem is the logic. The control logic is going to be complicated. And the other type of multi-port memory, which can be referred in this figure 13.4, it is called as a crossbar switch. So as the name implies, we have kind of a switch-like arrangements where we arrange all the CPUs in one column and all the memories in one row, and there will be interconnection structure, and this structure is going to be acting like a switch, and whichever switch is kept open or closed, accordingly we will be establishing the connection between that particular CPU and that memory. So the memory module and the CPU or the IO devices, they are connected with each other by means of a crossbar switch, and that's a diagram we have given here. And this is going to be the explanation for how actually this connection is going to be worked out. So if you just observe here, we have the concept of multiplexer. So what we mean by multiplexer, it is an electronic circuit which is available for us to select multiple inputs as one input. Okay, suppose for example, if you just observe here, we have multiple CPUs. Okay, CPU1, CPU2, CP3 and CP4, and if all these CPUs are going to be connected to the common memory, among this many, which one has to be connected with the memory? So from many to one, I have to convert. So for that purpose, I will be making use of the multiplexer. So multiplexer is a special electronic circuit which will receive multiple inputs and select only one input and then gets connected to the output. And if you take any memory module, it is supposed to have three important bus structures. One is the data bus, then the address bus, and then the control bus. So the control bus is responsible for carrying the control signal. So with respect to memory, the control signal could be a read operation or a write operation. And of course, memory enabled should be there. Only then that particular module will be enabled. So if I want to connect any particular processor to this memory module, they will be connected by means of this multiplexer setup, and this multiplexer is responsible for providing this arbitration logic which arbitrates across these many processors and select only one at a time and then gets connected to the memory module. So each processor will have their own data bus, address bus and control bus. So among these buses, which bus of the buses of which processor is going to be connected to this memory module is going to be decided by the multiplexer logic. So this is going to complete the discussion of the multi-port interconnection, and this is responsible for multi-switch or crossbar switch. And to do all these things, whenever we have multiple devices to be connected to one device, which to be selected has to be done by a special electronic circuit which is called as a multiplexer, and that is responsible for solving this arbitration problem. So the bus arbitration problem is going to be solved by this, and the same explanation is given here. So the multi-port memory system employs separate buses, okay, and then the module must have some control logic to determine which port should be connected to which memory module and for how long it should be connected. And if there is any memory access conflicts are to be there, then they have to be resolved by assigning fixed priorities to each memory port. So based on the priority, the connection will be established. And of course, the advantage is it is able to transfer data at a higher rate as it is going to follow multiple paths simultaneously. But it is having its own drawback. The drawback is the expensive memory. So the control logic, the large number of cables and connections is always required, and that may lead to an expensive memory. So the detailed diagram is shown here. So we have separate connections between the processor and the memory modules, and with the help of the separate connection, the cost is going to increase, but at the same time, it is possible for us to do multiple transactions at the same time. So I think we have discussed about the three connections. The rest of the interconnection structures, we will discuss that in the next session. Thank you. Hello everyone, welcoming you to this session to discuss about the topic on interconnection structures. In the previous session, we have discussed three structures, namely the multi-port organization, the time shared bus connection, and now we will just move on to interconnection structures with crossbar switch. Okay. So as the name implies, here we are going to have all the memories and the CPUs processors in one array, and they are going to be interconnected with the switch. Here the crossbar switch, as the diagram shows here, we have the cluster hierarchies, and each one is going to be referred as, each particular node is going to be identified as a cluster. And if you just expand and view how the cluster will look like, it is nothing but the collection of various nodes. And if you just expand how the node will look like, so each node is going to be of this type, where we will have inside each node we will be having a local memory and the processing element, which is otherwise known as the control unit, the processing unit, and then we have this network interface card. Okay, and all these things will be connected together, and they will be referring to the local memory. And this node will be connected with other such type of nodes to form a cluster, and all these clusters will be again connected together with the help of this crossbar hierarchy. So we have just explored the crossbar switch in terms of clusters, clusters, and then the clusters are nothing but collection of nodes. And if you take one node, it will be having all the processing elements, which can be referred as the processing unit, the control unit, and also the network interface. So these units will interact with each other, and they will have one local memory to share the information, and then it will be passed on to the other nodes in the network, and then such clusters will communicate with other clusters in the form of the crossbar switch. So this is how how, if you just observe how it will look like, this is how the view will be. So it consists of so many cross points, and these cross points are placed at the intersections between the processor buses and the memory module boards. The small square in each cross point is a switch that determines the path from the processor to the memory module. And of course, the advantage of this crossbar switch arrangement will be that it is possible for us to perform the simultaneous transfers from all the memory modules, because we have separate switch structure that connects the individual memory and the processor. We will be able to do the simultaneous transfer. Coming to the disadvantage, the hardware required to implement such switch can become quite large and complex. And figure shows the functional design of the crossbar switch connected to one memory module. So this is how we have already discussed this type of diagram. We have arranged the processors in one side and the memory in another side, and these processors and memories are interconnected with each other by a crossbar switch. And of course, this setup already we have discussed. If at all we want to connect many CPUs into one memory module, we have to use multiplexers, which will resolve the arbitration and which will decide what CPU or what device to be connected with the memory module and how long it should be connected. So we will be having the memory module connected with the multiplexer by means of data bus, address bus, read write bus, and the memory of course should be enabled, because we have so many memory modules communicating with the processor. So which memory is to be enabled for that particular point of time, that has to be received or activated by this means of memory enabled signal. And coming to this multi-stage switching network, we have two type of systems, as we have already discussed. One is called tightly coupled, another one is loosely coupled. The name tightly coupled refers to the memory which is going to be made common. So all the processing elements, processing units will be having a common memory, and these memory will be shared together, and so only it is called as tightly coupled. Coming to the loosely coupled system, each processing unit will have their own memory, which is also called as a local memory, and they will be always referring to the local memory, and the processing unit will interact with another processing unit by means of message passing mechanisms. So such type of systems is going to be called as a loosely coupled system. And coming to the basic components of the multi-stage network, we have two input and two output interchange switch. I think we can just see it from this diagram. Here if we just have, we have the two inputs A and 1, and the outputs are 0 and 1. So A can be connected to 0 directly like this, and A can be connected to 1 by means of this cross switch. And similarly B can also be connected to both 0 and 1. So with two input and two outputs, we'll have four combinations as mentioned here, and the same thing can be expanded to any levels. Accordingly, we will be providing the interconnection. And the basic component of the multi-stage network with two input and two output interchange, as we've discussed already, it has been expanded here. So obviously A and B can be connected to either 0 or 1 as per the requirement. So this is going to be a 2 by 2 switching switch, which is used as a basic building block, so that we can build or we can explore to any kind of multi-stage network. So for example, they have given another network of 3 levels, where we have the two inputs P1 and P2, which can be connected to 0 and 1, and like this we can have different tiers, different levels. And suppose if we want to have a 0 here, so this P1 will be connected to 0, and this will be in turn connected to another 0, and this will be connected here. So like this we can produce any number of binary patterns. If we have 3 levels, totally 2 power 3, 8 combinations can be addressed. Suppose for example, if we want to generate 101, so the P1 will be connected to 1 and then 0, so it should be connected to 0. 0 means it will be horizontal top connection, and then from this it has to be connected to another one. So like this we will be able to generate all combination of 7 patterns with the 3 levels. So the number of levels will decide how many binary patterns that can be generated. So this is another example of a crossbar switch, which is also called as an 8 by 8 omega switch network. So we can just traverse like this. So if it is 0 0 0, so all the 0 level will be connected, and similarly if it is 1 triple 1, all at the 1 level will be interconnected, and we can generate all the other combinations by providing the appropriate cross connections. So some request patterns cannot be connected simultaneously. That means any two sources cannot be connected simultaneously to the destination. So in a tightly coupled multiprocess system, the source is always going to be the processor, and the destination is going to be the memory module, and the path has to be established between this processor and the memory, so that the transfer of data can happen between them. And in a loosely coupled system, both the destination and the source are going to be both the processing elements, and because they are going to be the processing elements, each element will be having their own local memory. So only it is called as loosely coupled system. The last structure which we are going to discuss is called hypercube system, where we have different node structure which can be connected, and in this diagram we have just seen that it is an example for 1 cube, 2 cube and 3 cube structure, and this can also be made available as either loosely coupled system or hypercube architecture. Maybe this will be more clear if you just see this diagram here. So in the 1 cube connection network we will be having only 0 connected with 1, and in the 2 cube we will be having 4 combinations starting from 0 0 to 1 1, and with that we will be able to construct the 2 cube. And in the case of 3 cube we will be able to produce 2 power 3 8 binary patterns, and this will be connected like this. And suppose for example if the source node is 0 1 0 as depicted in this diagram 0 1 0, and the destination is 0 0 1, 0 0 1. So this is going to be the destination. So to reach this destination I can follow any path, and if this is going to follow this path, so we are trying to XOR the 0 1 0 and 0 0 1. If you do the XOR operation, it is going to be 0 1 1. So the hypercube structures for values of varying values of n equal to 1 2 3 can be interconnected in any of this form. And coming back to this details, the hypercube binary n cube multiprocessor structure is a loosely coupled system where we have capital N equal to 2n, where n is going to refer to the n dimensional binary cube. Okay, as the number of cube, if n equal to 1 we will be having only 1 here, and if n equal to 2 4, like this it will be expanded in powers of 2. Each processor forms a node of the cube, and it affects only a CPU but also the local memory and an IO interface. It contains the CPU and also a local memory with an IO interface. Each processor address differs from that of each of its neighbors address exactly by 1 bit position. That is an important point to be observed. I think in this diagram it will be clear if you just observe one node with another node, each one will be differing from each other only by means of 1 bit. So if you just observe here, if n equal to 1 it is going to be 0, and here it is 1. And in this pattern if you observe the neighboring nodes, see here this MSB pattern is going to be changed here, whereas if you observe these two, I think the LSB is changed from 1 to 0. And again if you observe the bottom two nodes here, the MSB is going to be changed from 0 to 1, and again in this I think the LSB is changed from 1 to 0. So if you observe, the adjacent nodes will differ from each other only with 1 bit change, and it is possible for us to generate the pattern like this. And similarly if you observe in this 3 cube model also, if you observe the adjacent nodes, there is only 1 bit change, and again if you observe here it is only the center bit which has changed. Like this it can be verified with all the combinations, and that's an important highlight of this structure. And the figure shows hypercube structure we have discussed, and the routing messages through an n-cube structure may take any form from 1 to n links from the source node to the destination node. So we have to develop a routing procedure, and that can be developed by computing the XOR operation of the source node address with the destination address. That's what shown here. So if at all I want to compute the path from 0 1 0 to another one, I have to perform this XOR operation. So if I perform XOR operation, I am getting 0 1 1. So that will help me to establish the routing procedure. The message is then sent along with any one of the access that are resulting the resulting binary value will have only 1 bit corresponding to the axis on which the two nodes differ. So corresponding to the axis with which 1 bit differ, the same thing here it has been occupied here. A representative of a hypercube architecture is the Intel IPSC computer complex. So this is one of the famous typical example for an hypercube architecture, and it will contain n equal to 7, so totally 2 power 7 128 microcomputers, and each node will have its own CPU, the floating point processor, the local memory, and the serial communication interface. So the connection between these adjacent nodes are going to be implemented by means of this XOR operation as mentioned here, by XORing the source node address with the destination node address. And after doing this XOR operation, the message is sent along any one of the axes that the resulting binary value will have 1 bit corresponding to the axis on which the two nodes differ from each other. So this completes the different interconnection structures, and to summarize, we have seen some of the highlights of the interconnection structures, namely the first category will be the time shared bus, where we are going to make the bus to commonly shared by all the processes, and it can form either as a tightly coupled or loosely coupled system. And then we have multi-port, where we will be having one-to-one connection between the processor and the memory. And the third one is a crossbar switch, which will arrange the processors and the memory modules in different rows and columns, and each interconnection of this row and column is going to be identified as a crossbar switch, and this switch will activate the transfer between the respective processor and the memory. The fourth category will be the multi-stage switching network, and in the multi-stage switching network we have seen how connection is going to be established between the two inputs and the two outputs. So you can connect the input either to 0 or 1. Like that we can connect any number of inputs to the appropriate levels, and different stages can be interfaced like that, and if the number of levels will decide how many combinations can be produced. And the last category which you have discussed comes under the hypercube system, where we have the nodes identified as all the vertices will be identified as nodes, and each node can communicate with appropriate memory, and they can also have the local memory interconnection. So this completes the discussion of the interconnection structures which are going to be adopted in the multiprocessor system. And of course in the crossbar switch we can have the concept of clusters, where the clusters are nothing but collection of nodes, and the nodes are nothing but the collection of the processing elements and the network interface which are interconnected with each other by means of local memory. So this completes the discussion of the interconnection structures. Thank you. Hello everyone, welcoming you to this session to discuss about interprocessor arbitration. So in the previous session we have discussed the various interconnection structures, and we have discussed that all these common structures are to be shared by multiple processors, and whenever sharing is going to happen, always there will be a conflict that who is going to use the common media. So how this arbitration is going to happen, that's what will be discussed in this session. And interprocessor arbitration can be provided by either means of single bus system or by multiple bus system, or it can also be done by data transfer method. So we are going to approach this particular topic under three categories. So if it is going to be a single bus system, how this address bus, data bus and control bus are going to be made use. And in case of multiple bus system, how the memory bus is going to make connection between the different processes, and is this memory going to be shared, or it is going to be distributed. And then how this IO bus will connect the local structure, and then how it will be connected with the common structure by means of system bus. Of course, this diagram can be seen in detail in this screen. The bus arbitration logic will decide how this arbitration is going to happen. So whenever a common resource is going to be shared by multiple units, who is going to share and who is going to use, how long it is going to use, and how it will be controlled, all these things has to be decided by some common procedure, and for that purpose we are going to make use of the bus arbitration algorithm. So this algorithm, as pointed out here, it can be static or it can be dynamic. So what we mean by static? Static means something which is fixed. So what is fixed here? The priority is going to be fixed. So if you just observe this diagram, we have so many devices and they are going to be arranged in the priority order. The first device will be enjoying the highest priority, and then the next, and then the next, like that we will be arranging in the decreasing priority order. Now there is a common bus here. This is the common bus, and this is otherwise referred as bus busy line. So whenever this bus busy line is high or active, it means that some process is making use of the bus system. So if at all another processor wants to use the same resource, then it has to wait because the bus is busy. So it has to wait till the bus is idle. Okay, so that is indicated by this bus busy line. Whenever the line is high, it means that some processor is making use of the bus for its own data transfer purpose. So if another device wants to make use of the bus, it has to wait till the busy line goes low. And the bus arbitration logic, it can be classified into two categories, broad categories, mainly static and dynamic. So we have so many devices. If these devices are going to be having the priority in the fixed order, it comes under the static nature. So if you just observe here, it is going to look like a daisy chain arbitration. Why? Because the first one will be always enjoying the highest priority, and if the first device wants to use the bus, it will activate the high line, and the arbiter will give control to this device, and it will be making use of the bus. Once it has completed its activity, then it is like a kind of a token system, so it will be passed on to the next device, and only if the first device which is enjoying the highest priority is no more in need of the bus structure, it will be granted to the next device in the priority order. And now if this device wants to use the bus, it will make use of it by again incrementing the busy line, otherwise highlighting the making the busy line high, or if it is not required, it will pass on the token to the next one. So like this the priority will be switched from one device to another device in a particular order, and this order of ordering of the devices based on the priority seems to be looking like a daisy chain, and hence this arrangement is called as daisy chain arbitration. and this is going to happen in a serial fashion, so it is otherwise referred as serial daisy chain arbitration. The any device which is in the highest priority is always going to enjoy the highest priority, and sometimes it may lead to starvation. So the one which is in the lower priority will be getting the chance only if all the other high priority devices are giving the chance to this particular device. So this is what we mean by static priority bus arbitration algorithm. Coming to the dynamic priority, as the name implies, the priority of the devices is going to change. I am not going to fix the priority of this. How this can be done? Here, what I can do, I can connect the last device with the first one. So if this connection is going to be made as a rotating pattern, it is going to be referred as the rotating daisy chain. So what will happen here? If this is going to have the highest priority for this turn, obviously it has to give the priority to the next device. So this will be enjoying the highest priority for the next slot. So like that, each device will be having the priority, and this priority is not going to be fixed. It is going to be rotated in the form of a daisy chain, because we connect the last device to the first device, and there is no more concept of having the first device in the highest priority and the last device as the lowest priority. Whichever is having the token for that particular period of time, that will be enjoying the highest priority. Once it has completed, it will hand over the control to the next device. So likewise, the priority is going to be altered among the devices in a rotating fashion, and hence it is called as rotating or round robin daisy chain priority mechanism. And another different type of mechanisms available here are time slice mechanism, polling, LRU, and FIFO. So coming to this time slice mechanism, each device in the which needs to share the common bus structure, each device will be assigned with a particular time slice, and this is going to be a fixed length time, and during the time that particular device alone will make use of it. If a particular device don't want to use a time quantum, it is going to be simply wasted. It is not going to be engaged with the next device. That is going to be the drawback of this. Or we can make an alteration in such a way that if a device doesn't want to make use of its quantum, it can pass on the control to the other device. So both type of arrangements could be there. That's what will happen in the time slice system. Coming to the polling method, so in the polling method, what will happen? There will be a kind of an arbiter which will keep checking with each device whether you want to share the bus or not. It will we will be polling one by one, and each device will be checked for the requirement. If it is requiring the bus arrangement, then it will be given grant. Otherwise, it will move on and continue to check with the next device. So there will be a common arbiter which keeps checking each device and whether you need the bus or not. If they need the bus, it will grant the bus, and it will activate the bus busy line. And if the device releases the bus, then it will be passed on to the next device. So by polling, by checking one by one, the bus will be granted to the one which needs, or it will not be granted to that particular device. So polling mechanism obviously needs a kind of an arbiter or a kind of a controller sort of arrangement which has to check the requirement of each device. Then coming to this LRU, that is least recently used. So whichever device has least recently used, that device will be given higher priority. Like this, we have different scheduling policies based on which we will be assigning priority in a flexible manner, and so it comes into the category dynamic priority scheduling, dynamic priority flexibility. And first in first out, as the name implies, the what device which enters this request in the first one, it will be maintaining a queue, and as and when a device initiates a request, that will be maintained in the queue, and the queue will be served in the first in first out order. So whenever a device wants to make use of the buses, it will automatically enter into the queue, and from one end of the queue, the devices will be getting the chances one by one. And this completes this dynamic priority. So as such, we have discussed the bus arbitration algorithm having two types, static and dynamic. And in static, we will be having the priority fixed, and the best example for this category will be the serial daisy chain arbitration, which is shown in this figure. And the next category is going to be the dynamic, where we make the priority flexible. How it is made flexible? Either by giving the times quantum for each one in a round robin fashion, or by means of polling method, where the arbiter will be polling the device by device, and it will be making the priority changing across the devices, and the least recently used will be enjoying the highest priority. It need not be always LRU, it can be even MRU also, it depends on the application and the requirement. Then comes FIFO, where the devices which needs a common shared bus will make a request, and it will add itself into the queue, and the queue will be serviced in one order. And then the last one is a rotating daisy chain, where we will connect the last device in the daisy chain to the first device, and by means of connecting this, we are not fixing the priority priority is getting rotated across the daisy chain. So we have different bus arbitration logic to take care of this procedure, and as a continuation of this we will just see how actually the arbitration logic is going to resolve the bus conflict. So we will be having two methods as mentioned in the previous diagram. One is called as serial arbitration procedure, another one is called as the parallel arbitration procedure. So in the serial arbitration procedure, it will be checked one by one. So that I think we will discuss with this diagram. So that same diagram we have already discussed. So the it will check the highest priority device. If it needs, it will, the arbiter will give the control to this device. Otherwise it will pass on the control to the next like that. So if it is going to be arranged in this serial fashion, and if the arbitration procedure is going to be invoked one by one in a serial order, then it is coming under this category serial arbitration. Whereas in the parallel arbitration logic, we have all the bus arbiters arranged in one form, and then we have the priority encoder and the 2 by 4 decoder. So we have the bus busy lane. So which device has to use the bus and for how long it has to be used has to be decided by the bus arbiter, and this arbitration logic is going to be operated in a parallel fashion, and so only it is called as parallel arbitration logic. For this purpose we also make use of an 4 by 2 priority encoder and a 2 by 4 decoder to resolve this purpose. So each bus arbiter will have some request, and it will receive the request, and based on the arbitration logic it will decide whether to give the control or not. If it decides to give the control, it will activate the bus busy line, and after completion this will be receiving the acknowledgement by which it will withdraw the request. So this is going to be the procedure that is going to be adopted for parallel arbitration logic. And as already I have discussed, dynamic arbitration algorithms can be categorized based on the parameter used for deciding the priority. Is it going to be a time slice assigned for each quantum, for each device, or it is going to be a polling procedure where the arbiter is going to check one by one, and then the LRU, it is based on the time whether it is recently used or not used, and then the FIFA also the entry time, the first which is entered for the request, it will be put up in the queue and the queue will be served. And then we have the rotating daisy chain where the last device will be connected to the first, and thereby we are just making the priority also to rotate. So this is going to be the discussion for the synchronization, the communication procedure, and with the various processor in a multiprocess system has to communicate with each other. That is going to be an important activity. For communicating only, we are going to make use of either the shared resource or a dedicated resource, and this communication can happen by initiating the request, or it can be done by means of passing on the messages. So we can have separate procedures to deal with the communication process. It can be making use of the mailbox facility also. The status bits will reside in the common memory, by which we will be able to appreciate the status of each device, whether they need to use the resource or not to use. And the receiving processor can check the mailbox periodically, and then the response time of this procedure can also be a time consuming activity, so it is going to rarely be adopted. A more efficient procedure for sending the processor an alert message is by means of raising the interrupt signal. So this is going to be an efficient procedure, because in polling it will be wasting its time and keep on checking the status of the device, whereas if it is going to be an interrupt initiated, the device which wants to make use of this common mechanism or sharing mechanism, that will initiate an interrupt, and upon receipt of the interrupt it can be handled. And there could be a conflict also among these resources, and how this conflict is going to be resolved, it will be taken care by the operating system. And there are a general in multiprocessor setup, there can be master slave configuration, or it can be a separate operating system or distributed operating system to decide all this multiprocessor setup. And in the master slave mode, one processor will always act as a master and execute the operating system function, and the slave will be controlled by this master. And if it is going to be dedicated separate processor system organization, each processor can execute the operating system routine whatever it requires. And in the case of distributed operating system organization, the operating system routines are distributed among the available processors, and however each particular operating system function is assigned only to one processor at a time, and hence it is always referred as floating point operating system. So coming to the loosely coupled system, we have no shared memory for passing the information. As we already discussed, if the memory is going to be shared, it comes under the category of tightly coupled, and if each process is going to have its own local memory, then it is going to be called as loosely coupled system. So there is no shared memory for passing the information, and hence the communication between the processor, how it is going to happen, it is always done by means of passing the message, and this message will be passed through IO channels. And whenever communication communication is going to be done by passing the messages, then who is going to initiate the message passing mechanism? That is going to be an important activity, and usually the master will initiate the process, and the communication is going to be efficiently done by means of adopting appropriate routing protocol, and the processor speed, the data link speed, and all the topology of the network altogether will decide the communication speed or the efficiency of the interprocessor network. So this completes a discussion of the loosely coupled system, and also the arbitration logic, how it is going to be carried out in the sequential fashion and also in the parallel fashion, and in within which we are going to further classify as a static procedure or as a dynamic procedure. So as a continuation of this topic, we will just discuss how the synchronization is going to happen in interprocess communication mechanism. Thank you. Hello everyone, welcoming you to this session to discuss the concept of inter-processor communication and synchronization. So in the previous sessions, we have discussed how these processes are going to be interconnected with each other, and now we will discuss about how communication is going to happen among these processes and how the control information is going to be exchanged. And to start with, we should be aware of this cooperating processes always have to execute their work in a synchronized fashion. So what we mean by synchronized fashion is, if one processor is using the resource, obviously the other process should give away. If more than one makes an attempt to share the same resource, it may end up in a conflict. So in such cases, how we are going to synchronize the activities of the cooperating process. So that is going to be discussed in detail about this inter-process synchronization. And usually we will try to enforce the correct sequence of processes. Only then the mutually exclusive access can be made to access the shared information. So in a multiple process system, more than one process will make an attempt to make use of the memory, and if it is going to be for read operation, we can allow all the process to read. It's not going to create any issue. But in case if it is going to be a write request, then if I allow more than one processor to share the same memory, obviously it will end up in a conflict. So to resolve that, we have to go for a synchronization mechanism that will decide who is going to use the resource and for how long it is going to use the resource. So in all the multiprocess systems we have discussed so far, we have so many such mechanisms available to synchronize this activity. So we have the low level primitives which are implemented in the hardware. So anything which is implemented in the hardware is going to be more efficient in terms of speed, but of course there will be some lack in flexibility. And there are some primitives which are available which can enforce mutual exclusion by means of some complex mechanisms implemented at the software level. So what we mean by mutual exclusion, more than one attempting to share the resource and only one will be allowed, obviously the others will be controlled not to enter into that common space. And there are other mechanisms like binary semaphores which are also available to enforce this mutual exclusion policy. Now we will just see how this mutual exclusion is going to happen. So before that, we will just refresh some of the key terms related to this interprocess communication and synchronization. So the first property which we always expect is that we have to provide an orderly access to the shared memory. So if resources are going to be shared by many processes, who is going to use and for how long they are going to use, this sequence order has to be determined. The mutual exclusion will take care of that, and also it will take care of protecting the data from being exchanged simultaneously across the processor. And one more important topic which we have to be clear is that the critical section. So what actually we mean by critical section? It is a program sequence that must complete execution before another process accesses the same shared resource. So if more than one process wants to use a particular portion of a program, it has to be done in an exclusive manner. So only one should be allowed to enter. And after this particular process completed its activity, if it is leaving that resource, only then the other processor should be allowed to enter into that portion. Any portion which is going to critically affect the result, if we allow multiple process, is going to be identified as critical section. So who is going to enter into that and how we are going to ensure mutual exclusion is going to be provided by some mechanisms available for it, and one such mechanism is called a semaphore. So semaphore is nothing but a binary variable, and that binary variable will act like a lock. So suppose for example I have only one resource with me and more than one is competing for that resource. So somehow or other I, based on some priority or some scheduling manner, I decide okay this process can start using this resource. And once a processor is starting using to started to use a resource, it has to lock the resource. Only if it is locked, it can prevent other process from entering into that resource. So that lock is nothing but a semaphore, which is a binary variable. It is not a hardware, it is a binary variable. So whenever a processor makes an attempt to enter into a resource, it will immediately set the binary variable to indicate that that resource is with its control. All the remaining competing processes has to wait till the lock is released. So that is going to be implemented by the concept of semaphore, and it is called as a binary semaphore because if it is 1 it means it is in use, if it is 0 means it is free. So whether it is locked or it is released, so that is going to be indicated by the binary state. And the testing and setting of this semaphore itself is going to be a critical operation because more than one processor is going to check whether the lock is locked. Okay, so in that case, the testing operation also has to be done in a single indivisible operation. What we mean by single indivisible operation, it is a kind of an atomic operation. Atomic operation means it has to be done till the end. So in between, nobody should interrupt. So when a processor makes an attempt to check whether the critical section is under use or not, that is testing whether the lock is under locked condition or released condition. So that operation itself has to be an indivisible operation. So for that purpose, we always use some test and set instructions, and this can be implemented as a hardware lock mechanism also. And whenever the instruction is going to execute this test and set lock, it has to be executed in two memory cycles. Why? Because first it has to read the status of the memory, and only if it is not locked, the new process can acquire a lock by setting the value to 1. If it is already locked, it has to wait. So to do this, to check this operation, always it will consume two memory cycles. And note that the lock signal must be active during the execution of the test and set instruction. When a process is testing the status of the lock, at that time no other process should make an attempt to test. So this test operation has to be done only by one process, and it is going to be an atomic operation. So this is a key point which we have to observe in the inter-process communication and synchronization. And now, with respect to communication, as I mentioned earlier, we have talked about shared memory and no shared memory. If it is shared memory, we will call that as a tightly coupled system. And if it is not shared, it is going to be called as a loosely coupled system. If it is going to be tightly coupled, all the memory, the common memory is accessible to all the processes. So it acts as a message center, which is similar to a mailbox. One processor, if it wants to communicate with another processor, it will just type the message like a mailbox, like in the common memory, and the other process which is also sharing the same memory will be able to read the information. Coming to this loosely coupled, there is no concept of common memory, so obviously there is a need for passing the message from one processor to another processor. And with respect to synchronization, we have to ensure that mutual exclusive access is available, and by mutual exclusion we are able to protect the data because at any point of time only one processor is allowed to update the data. If more than one processor makes an attempt to change the data, it is going to end up in a chaos. So that should not happen. So mutual exclusion has to be ensured. So this is one of the prime requirement for this inter-process synchronization, and usually this mutual exclusion is going to be implemented by means of semaphore. Already I have informed semaphore is nothing but a binary variable which will always reveal the status of it, is like a kind of a indicating the status of the lock. If it is 1, it will indicate that it is in use. If it is 0, it indicates it is free. And critical section is once it has begun, it has to complete the execution before another process access this region. And hardware lock, it is already discussed, so it is nothing but a mechanism which is available at the hardware level that can ensure this synchronization process effectively and efficiently. So the same thing we have discussed here, the communication, the shared memory, the loosely coupled system, tightly coupled system I have informed. So various processor in a multiprocessor system must be provided with a communicating facility, and this communication is usually established by means of some input and output channel. So whenever the processor wants to communicate something, first it has to frame that message. So it has to structure the request, what is the message it is going to pass on, and by means of the procedure is it going to do, and always it will places this information in the mailbox with respect to the tightly coupled system. And the status bit will also be there, and the status bit is going to be a good indicator of whether a particular portion in the memory is in use or not, or free, relatively free. So the receiving processor can always check the mailbox periodically for any message meant for it, and if it is there, it will start consuming it. Okay, the more efficient procedure for sending the processor to alert the receiving processor is by means of an interrupt signal, because every time if a processor is keep on checking whether I have received any message from another processor, it is going to be a waste of time. For that option, the efficient mechanism could be that if a processor is going to receive a message, it can be interrupted by the sending processor. So upon receipt of the interrupt, the processor can just look into the mailbox and can make use of the messages. And again, if the shared resource is going to be accessed by multiple, obviously there will be a conflict. So to avoid this conflict, we have to assign the scheduling sequence. So who is going to access the resource, that order has to be priorly determined. And we have three organizations that have been used in the design of the operating system for with respect to multiprocessor. So one method is the master slave configuration, where one processor will act as a master and all the remaining will be the slave, and the master will have the control over the remaining processor. And then we can have separate operating system running in each processor, and they are going to be autonomous in nature, and they will be cooperating with each other to get the work done. And the third category will be the distributed operating system, where the resources will be distributed and it will be scheduled by the respective operating system. So in master slave mode, as I told, one will be the master and the other remaining will be the slave, and the master is going to decide everything. And in the separate operating system configuration, each processor can execute the operating system routines whatever it needs and get the work done. Whereas in the distributed operating system organization, the system routines are distributed among the processors, and however, each operating system function is assigned to only one processor at a time. It is also referred as a floating operating system. So this completes a discussion with respect to tightly coupled configuration. And coming to loosely coupled configuration, there is no common memory. So there is no possibility for passing the information through the memory. So for such cases, we have to frame the messages, and the messages have to be passed on from one processor to another processor. The communication is initiated by one processor and it is going to reach the other one, and how it is going to be informed is by means of synchronizing signals. The communication efficiency of the interprocessor communication system, it always depends on the routing protocol whatever we are going to use. It also depends on the processor speed, the data link speed, and the topology of the network. So all these factors will decide how this communication is going to happen in an effective manner. Coming to the synchronization part, as I told, we are going to make use of the semaphores, and multiprocessor system usually include many mechanisms for providing the synchronization, out of which the common popular method is going to be the binary semaphore. And apart from this binary semaphore, we also have the concept of counting semaphore, where it will keeps counting on the number of processors who are waiting for the resources. At any point of time, only one processor will be allowed to access the resource, and whoever has gained the control, that will be using the resource. And after its completion, it will release the lock, and the token will be passed on to the other waiting processes in turn. The mutual exclusion with semaphore, it is necessary for the data to be protected, because if more than one processor makes an attempt to change it, then it is going to end up in an inconsistent value. So that should be ensured. So any mechanism which is going to be adopted for mutual exclusion has to ensure that the processor, only one processor will be allowed to change or allowed to update the resources available in the critical section.
A critical section, already I think we have discussed about the critical section. So when the semaphore value is going to be equal to 0, the shared memory is available to any requesting processor. If the processor access the shared memory, it means that it is executing the critical section, and in that case it will set the semaphore to indicate that it is making use of that particular portion, and then it will release that settings after completion. Usually the other processor who is waiting for the resource will just check for the availability by means of testing and setting the semaphore value before entering and exiting the critical section. A hardware lock can also be provided, and this will generate a signal which will prevent other processor from using the system bus as long as the signal is active. And we also have the semaphores by means of test and set lock instruction. So there is an important hardware mechanism available which is going to be referred as test set lock, that is nothing but TSL. So what actually this instruction is going to do, if you just observe here, the test and set while locked operation will perform first testing of the status. To test the status, it has to read the memory variable m of sem, and after testing, if it seems to be 0, it means it is not in use. Then whoever wants to use that critical section will set that semaphore value to 1. So it will test for free, and if it is free, it will set it and then it will use it. So this is going to be an indivisible operation, and it is going to be done as an atomic operation. So this completes a discussion of the interprocessor synchronization, and the communication is going to happen only in case of the loosely coupled organization. In tightly coupled organization, the memory will take care of. Thank you.